you throw the term nano in front of a word, half of people are going to be very excited about it, and the other half of people are going to pull an Elon Musk and roll their eyes. While nanoplasmonics as a field is about using teeny metallic particles, like little spheres of gold or copper, to dramatically enhance the interaction between light and matter. And these effects only happen if these particles are much smaller than the wavelength of the light. And since visible light has wavelengths in the hundreds of nanometers, that means that these particles need to have sizes of, say, 20 nanometers. In other words, the title of nano is well earned because it's an effect that doesn't exist if they were any larger. There is no field of, say, microplasmonics. But okay, nanoplasmonics is about using metallic nanoparticles to enhance the interaction of light and matter. That sounds a little vague, but these tiny metal spheres allow one to do some extremely incredible and very useful things. In fact, there are so many useful things you can do that I literally couldn't even fit it all in one video. So over the next 2 videos, we're going to be looking at the applications of these miraculous little metallic spheres. However, when discussing the behavior of these things, I'm only going to lay down, like from on high, their key properties. I'm not going to explain why they behave this way here. Instead, the 3rd video in this series will do that. So applications of nanoplasmonics is this video and the next. The physical origins of this behavior is then the video after that. I know, 3 videos, but take it as a sign that there is a lot of cool stuff we need to talk about. So okay, let's get started. In your basic nanoplasmonic scenario, you have light, like that from say a laser, which is shot onto these little metal particles. These particles might be suspended in a liquid, or they might be part of a rough surface, or they can even be placed on a surface in an orderly way. And when these nano-sized metallic particles are illuminated by this often monochromatic light, they have 3 important properties in how they are affected. Firstly, this light excites what are called plasmons in the nanoparticles. What are plasmons? Again, that's the upcoming 3rd video. But as a result, these plasmons dramatically enhance the electric field in a small neighborhood around the particle. So they're like little nano antennae or amplifiers that take the energy in the electric field of the light and redirect it to create their own field, but just in some small area around themselves. But that field is way stronger than the field of the incident light. This is called electromagnetic enhancement. So it's like the impinging light starts the party, but once the plasmons in the metal get involved, it gets dialed up to insane rager. But by how much is this field enhanced? Often by a factor of thousands, or even hundreds of thousands. It's an enormous boost. So that's our first key property. They boost the strength of the electric field in their neighborhood. The second property is that this plasmonic response of these nanoparticles doesn't treat all wavelengths or colors of light the same way. In fact, if you plotted the strength of electromagnetic enhancement versus wavelength, you'd find there's something called a plasmonic resonance at a specific wavelength. So in a sense, these particles are like little singing, like wine glasses, where there's one specific frequency that is a natural resonance for them and makes them sing, so to speak. Though, remember, we're talking about light here and not sound. Now, the frequency of light at which this resonance occurs isn't some universal property. It's not some fundamental property of the cosmos, but rather it depends on things like the material property of the metal, the shape and size of the nanoparticle, and importantly, and this is our 3rd important plasmonic property, it depends on the environment around the nanoparticle. If I have a metallic nanoparticle in a vacuum, and it has a certain plasmonic resonance, and then I go and place it in, let's say, water, the frequency of this resonance will redshift. It'll move to a lower frequency. Another way of saying this is that if I illuminate this particle with white light, which contains all colors, its color will shift depending on its shape and its surroundings. So the key properties are that when a metallic nanoparticle is illuminated, 1, it creates a region of dramatically enhanced electric field directly around it. 2, it has a resonance to this electrical response, a signature frequency depending on its material and shape. And 3, this resonant frequency shifts in response to changes in the medium around it, the medium it's immersed in. So let's talk about applications. But remember, in this video, we're only doing about half of the applications. In the next video, we're going to talk about sensing and scanning applications that mostly are based on this 3rd property. Here, we're going to talk about what you can mostly do with these 2. One way you can exploit these properties is to basically recognize that they allow you to create hotspots of an electric field, concentrating it into a very small area around that nanoparticle. This concentration of the electric field can then also drive absorption of the light, which then leads to basically a localized heating effect. One particularly dramatic application of this is using metallic nanoparticles. You can literally boil water using concentrated light at temperatures far below boiling. When the nanoparticles enhance the field of the laser light, it creates a bubble where absorption of light is dramatically higher and thus heating is similarly enhanced. You therefore get little bubbles of vapor that are nucleated by these particles and float out of the water as steam. Of course, you don't have to only do this with water. This allows one to, for example, catalyze a chemical reaction using light at illumination levels where it naturally wouldn't occur. But going back to this heating of water idea, this also has applications to create so-called hybrid photovoltaic thermal cells, or HPVT. Solar cells for power generation don't actually use all the wavelengths of light that the sun emits. In fact, they don't use any light at all above a certain cutoff wavelength, which is related to what's called the bandgap energy. Well, houses need power, sure, but they also need hot water. And if the solar cell isn't using these wavelengths anyway, why not a layer on the top of the cell with nanoparticles suspended in a transparent fluid? The idea being that the nanoparticles are engineered to have their plasmonic resonance in the range of unused wavelengths, and thus drive absorption heating of the fluid. The wavelengths that the cell does use pass through unaffected. There's also yet another way you can use this localized heating trick. What if you coat your nanoparticles in some biological molecule that will only bind to another very specific biological molecule? You then create a scenario where your nanoparticles will accumulate in areas where your targeted binding molecule is concentrated. Given this, there is an idea that if one can find a compound associated with cancerous tumor tissue, then you've got a potential cancer treatment on your hands. The idea is, because gold and silver and such are non-toxic metals to the body, you inject them into a patient and they'll be inert. However, because they're coated in a molecule that binds to some targeted tumor compound, they'll accumulate in the tumor region. Then you use a low-power laser in a wavelength that is transparent to human tissue, like say the near-infrared, and if the nanoparticles have their plasmonic resonance in that same range, they will start to boost absorption and become very, very hot. Thus, even though the laser is weak and harmless, and even though the tissue is largely transparent to it, you're going to get localized burning of the tumor tissue. No radiation, no chemotherapy, just microscopic flecks of gold, a little light, and heat. But okay, enough about this localized heating effect. I actually only scratched the surface on it, but I ain't got all day. So let's shift and look at another set of applications that are based on different physics. As we discussed, the resonant frequency of a plasmonic nanoparticle is determined by a couple properties, including its environment and its shape. In a nutshell, this means that when you have an array of these nanoparticles, and you illuminate them with white light, you can tune how they reflect that light based on shape or environment alone. You can in fact create all the colors of the rainbow just by making little plasmonic nanodots all made of the same material, just with different shapes. Now, an immediate and obvious application of this is to make static, reflective color displays. Because these nanoparticles are so small, you could literally make a colored image with 100,000 dots per inch, or DPI. You illuminate it, and a very high-resolution color image is shown. And because these are basically just tiny metal balls, they can be embedded in something like a polymer to make a flexible display. However, hearing that, you may realize I basically literally just described a technology we've had for quite some time. It's called taking what are called inks or paints and putting them on a substrate called paper or canvas. It's not exactly new. So this idea might seem like a waste of time, but something we're working towards is to be able to dynamically change the plasmonic resonances of the paper. Then we would basically have so-called electronic paper. Think something like your Kindle or other e-reader, except in color, much higher resolution, and potentially flexible. Now that's the idea, but unfortunately, don't expect these plasmonic displays to hit the shelves soon. There are literally dozens of suggested ways of how this plasmonic resonance could be dynamically switched, but none of them are ready for the showroom floor yet. One example is to use a voltage to literally control the reversible deposition of silver onto a silver nanoparticle. In other words, your silver nanoparticle is embedded in like a gel containing silver atoms, and by using a voltage, you can tease those silver atoms to deposit on the surface of the nanoparticle. As a result, the nanoparticle basically just gets bigger, and its plasmonic resonance then shifts. If this deposition is reversible, you can then undo this accumulation by reversing the voltage. Another idea is to combine these plasmonic particles with what are called electrochromic polymers, which are polymers whose color or electrical properties change when electric field is applied. These polymers can actually be used by themselves to make dynamic displays, but they have a number of drawbacks, such as the need for thick films and high voltages. But by exploiting the field enhancement effects of nanoparticles, maybe it's possible to overcome both of these drawbacks by concentrating the field, so less voltage is required in a thin film. As I said, there are literally dozens of other suggested ways of making such screens, and I encourage you to explore for yourself. But hopefully that's enough to maybe just give you an idea. So in this video, we introduced the basic properties of nanoplasmonic particles, but we're saving a discussion of their physics for an upcoming video. We also discussed some applications